again. And I'm Chris, and I'd like to welcome you all to the first official webinar with the Biotensegrity Archive, with the SM11 Biotensegrity Archive. And so this is a big deal for us because we're reaching out, fulfilling our mandate of really raising awareness about biotensegrity and helping to educate people. Most of us feel a little isolated and want to learn more. So the archive is trying to give everybody opportunities to learn more and to share that learning. I would like to welcome archive board members and biotensegrity pioneers, Graham Scarr and Susan Lowell. They both work closely with Dr. Stephen Levin, who is an orthopedic surgeon, who first recognized the importance of biotensegrity to living organisms. And they're both authors. Graham's book, Biotensegrity, the Structural Basis of Life, and I have it here, but maybe it'll be backwards for you guys. It really is a groundbreaking book, and it's on its second edition, which if you don't have, I recommend you get. And Susan's book is upcoming with Handspring Publishing as well. It's called Everything Moves, How Biotensegrity Informs Human Movement. And we're really excited to see that come to be published. Susan has an MA in Human Development and Education with a focus on kinesthetic learning. She's certified as a level 3 Tai Chi instructor with the American Tai Chi and Qigong Association. And is a certified Flex Aware teacher also. Since 2012, she has been assistant to Dr. Stephen M. Levin, originator of the biotensegrity concept. And she's also the co-founder and head organizer of the DC BIG, that's in Washington, DC, the Biotensegrity Interest Group that was established in 2012. Graham Scarr is a master model maker. Working with Stephen Levin, he's developed new models, many new models that progress our understanding of the structure, function, and relationships in biology. He's a chartered biologist and osteopath with a particular interest in structural mechanics, fascinated by the numerous examples of geometric patterns and shapes in nature. He's been researching their significance over many years. As a graduate in microbiology, and after spending several years developing his skills in a bacteriological research lab, he's now part of a specific interest group looking at the significance of the biotensegrity concept to biomechanics and clinical practice. And Graham is at the forefront of current thinking about this subject, as is Susan. Graham's a fellow of the Linnean Society. Is that pronounced properly, Graham?
That's fine, yes.
Biology, and he's published several papers as well as the book. So we're going to start off with Susan, and I'm going to just ask you to take it away, Susan.
Great. So there's a PDF that I think you may have access to. It's not important that you look at it now, but you can if you want. I'm sort of free form talking off of the ideas that I wanted to go over today. And I just want to say, these are my reading glasses. They have little tiny holes in them. So I'm not really trying to look mysterious. It's just a way for me to see based on the camera principle. Very biotensegrity aware technology as far as I'm concerned. So my main theme, functional structure is not arbitrary. Graham and I were talking yesterday, and one of the things that happens is people get their tensegrities and they say, okay, these are the bones, these are the tendons and the ligaments. Thank you, see you later. And a lot of us are sort of standing here saying, no, wait. All you did was get to the front gate of the house. You didn't, there's so many wonderful things. So I always come back to the model whenever I have a question. I mean, of course, we have our written resources, which are wonderful, but I always come back to the model. You will see lots of triangles in your model. We need to understand these. We're never looking specifically for triangles in the body, although we have the scapula, triangular kind of shaped bone and that sort of thing. Instead, we want to understand these triangles as force vectors. A force is just an interaction. So these are lines of interaction. If you just tune into where you are right now, your physical center has a really important relationship with the center of the earth. And the gravitational pull on your body is from your center to that center. It's a straight line. If you jump off the couch to the floor, you don't kind of, I think I'll wobble a little to the left or the right. There's really one option, and that's that straight line. And I'm going to tilt my screen so you can see what I have here is a little ball, because we also have in our tensegrities a sort of spherical quality. The icosahedron is very efficient shape in terms of materials, and so is the sphere. And that's why bubbles are round, and planets, and all kinds of other things. So here is a ball in a bowl responding to gravity. There's another little sphere. And now they're trying to get to the center. As soon as I add 3, this happens. I can disturb it. This will always happen. It will always be come to a triangle. It will never not do that. A triangle is, we could talk for probably a week just on triangles. Definitely we could do a whole hour. But a triangle is a structure that is a low energy structure. This can wiggle, this can move around, it can do all kinds of things. As soon as it becomes a triangle, all of a sudden it's still, it's quiet. And that's not with, I didn't add glue, no bracing. It's just the characteristic of the triangle. So triangles are interesting. You see them a lot in nature. Now you'll see a little space. As I add more, everybody see the bottom of the bowl? You see this pattern. That pattern is ubiquitous in nature. There's a hexagon. There are the triangles inside the hexagon. I can disturb this. And this is what I mean by that the functional structure is not arbitrary. We're not putting these things together with our intentions, saying, oh, that's pretty, I think I'll make it like that. No, nature is doing this. This is just how stuff falls together. It is the way of things. And there is just nothing I can do to get around it. And I don't necessarily want to get around it. Now, if I add enough, you'll start to see, Graham, I think this relates to the Penrose tiling, if I can get it to happen. But you'll start to see when I disturb the mix, little variations will arise. She said with confidence, because they did the last 600 times. But anyway, you'll start to see that arrangement of 4. Sometimes you'll see a ring of 5. There's a pattern that's different. You see, there's now kind of a flower of 4 here, here, here. But then it goes back to being triangulated, like here. When I disturb it, it's back again. And so every so often when I do this, we almost got one that time, there will be 5 in a circle. So it's just really interesting. There are rules of structure, but there's enough wiggle room for there to be some variety, which is, I think, what makes all of us a little different. So that's just something about spheres, efficiency, force vectors. And this is all stuff that we get led to. These are all pieces of information we're led to when we start with this, when we start with the tensegrity. Now, Chris, do you have any idea how I'm doing on time?
It is now 11:13.
So we're okay.
Yeah.
Right?
Yep.
So Kim Thompson is with us today. She's a member of DC Big. And I have to tell you, people ask, how can I use this information when I'm working with a body? Because a lot of people who are into this are professional body workers and such. So I'm stealing this directly from Kim, this insight. It's so fabulous. We had a DC Big meeting, and I brought, and this is a rubber band tensegrity that I built for another project. But anyway, I brought a 3-strut tensegrity with me, and we were passing it around. And one of my Tai Chi students had come to the meeting, and she broke the string, right? She broke the string, and the whole thing went flat, and she was horrified. And there's this woman horrified, and Kim saves the day and says, this is showing us that if there's a problem like two bones touching each other, and we think we can solve that problem by going into that space and trying to expand it, we're not seeing it systemically. We're not aware of the tensegral nature of the body. If we just restore the structure, the space is restored. And I think that's what a lot of you are doing when you're healing the system or helping the system find its way to its own healing, is you're helping it restore its natural order that comes undone. Okay, now another thing we're led to, we're going to do auxeticity. Big word. Auxetic things expand and contract in all directions at once. So unlike something that we're used to, like, just some sort of an orb where if I squish it down a ball of putty, it gets flatter and it gets wider, and then I can roll it up into a ball again. If I pull it, it
Susan,
gets longer and it gets thinner.
Put it down just a little.
Oh, sorry.
Perfect.
So what happens with a tensegrity structure is that it has a negative Poisson's ratio. That ratio we're used to is called a Poisson's ratio. This is a structure which expands in all directions when you expand it in any two. Now, why do we care? So I was doing a sort of online consulting with a yoga teacher, and in her school, she had been taught that as you inhale, your lungs get wider and your spine gets shorter. And then as you exhale, your ribs get smaller, your torso gets thinner, and your spine gets longer. If all you know is the possibility of that Poisson's ratio with that roll of clay, if I squish the ball of clay, it goes flat and then I roll it up again. You don't know about this as a possibility, right? Then you can't really, you're not really free to consider your own auxetic nature, where you can inhale and everything can expand in all directions. and you can exhale and everything can condense in all directions. So that's just another thing that Tensegrity leads us to. And then, do I have like 3 or 4 more minutes?
Yeah.
Great. Okay, great. Auxeticity is a characteristic of materials that are classified as soft matter. So we get into all these different things when we're studying biotensegrity. And I just want to give you the big picture and why I think it's useful to us. So auxetic things are part of, that's a quality you'll find in some materials that are classified as soft matter. When I grew up, and I found this recently on a college website, 3 states of matter: solid, liquid, gas. As it turns out, probably almost everything is none of the above. Everything biological is none of the above. And that's where soft matter comes in. Now you can look up Oobleck, O-O-B-L-E-C-K, and check it out on video on YouTube or something. And you'll see people running across swimming pools and then stopping and then sinking. It's a cornstarch and water mixture. A lot of you have already seen that. What I wanted to show you today was just 2 things that are soft matter oriented. And all of these things are models, right? This is a model. So this is a can of beans, which is kind of heavy. And about 2.5 hours ago, I cut some grapes, red grapes, in half, and I inverted them onto a paper towel so that you can see there's been a little bit of a color bleed. But I have to tell you, this paper towel is substantially dry. The grapes are pretty much intact, still juicy. The can's been squishing them for a couple of hours. And this is a direct steal from Dr. Levin, from Steve. And, you know, he says there's no wet water in the body. And so these living things, these grapes, if there was wet water, we'd be seeing it all on the paper towel, especially with pressure over time. It's not there. Another thing about soft matter, and you'll see this if you look at the Oobleck, but it is transmutable. The state of it changes. This is a really simple experiment that I recommend you do at home. You need to generate a bunch of static electricity. And you need to have pre-mixed some cornstarch with oil. And that mixture is electrorheopectic, right? What it means is that this electrorheopectic slime, and I'm just going to start it in a stream. Let's see. Let me get the camera closer to it. Don't go away, balloon. Ah!
Uh-oh.
Uh-oh. Okay. So what happens with electrorheopectic slime is that basically it goes from being very liquidy. Ooh. See it?
Cool.
Take the balloon away. Not only is it getting solid, it's coming toward the balloon. Can you see that?
Mm-hmm. So what's going on there, Susan?
What's going on is the electrical charge from the balloon is enough for the state of the matter to change from something that we would identify more as liquid to something we would identify more as solid.
Wow.
It's also breaking the laws of gravity, right?
Mm-hmm.
So I just figured that anything, something that's inert and not even alive can do, any of that physics that allows this to happen is available to biology.
Mm-hmm.
Not that every creature might be making use of this, but some of you manual therapists will talk about how, you put your fingers on somebody and everything's very stiff. And then all of a sudden, everything lets go. We know that pressure and piezoelectricity and stuff, we can have pressure change electrical charges in the body.
Mm-hmm.
And introducing an electrical charge to this, inert slime causes state changes.
And all biological organisms are contain
Are
soft.
transmutable.
Yeah.
Oh, sorry, go ahead.
Yes, all living organisms are made of soft matter, which behaves in ways of which that's just an example.
Exactly. And so
Right.
when Graham has these great models where he shows you a tensegrity and he says, yeah, and remember that at any point, the strut can become the string and the string can become the strut, right? Plus that it's all hierarchical, where any one of these lines is really like a tensegrity mast. So you get a hierarchical understanding. I'm just telling you, we're doing crazy bottomless pit studies here, everybody. So please come in. We need your help. This is a new and emerging science. We're still learning. We study shapes. From the triangles, we get the tetrahedrons. And then I've been making this tetrahelix, which is all tetrahedrons, which is all straight lines, but there are the curves. 6 helices inside of one tetrahelix.
The
So
curvature emerges out of it.
the curvature emerges. All you do is make one tetrahedron stuck to another, and this happens. 6 interwoven, interembedded spirals. So anyway, biotensegrity is a crazy world, and welcome to it.
Brilliant. Brilliant.
I'll leave it to Graham, and then if you have any questions, I think my email is also on that sheet.
Thanks, Susan. And we'll add your email at the end of the webinar as well. Yeah, you wanted to put in a get up and stretch here.
Oh, yes. I thought we should have a bio break.
Bio.
Get yourself.
Okay, so I could actually use a bio break myself. So Graham is going to set up to do your PowerPoint. Are you, Graham?
Yes, yes.
And meanwhile, Susan, if you click on your Q&A, you can look at, I answered a couple of things. You can look
Oh, cool.
Written, and if you want to respond, you can. I'm going to disappear from. Okay, and I think I need to unpin you.
There are 2 questions here, and I'm going to go with Steve Schafferman's. Hi, Steve. Also a member of DC Big and the originator of the FlexAware movement system, which is wonderful and really sort of a biotensegrity aware kind of practice, which I love. I said characteristics are available to biology. Yeah, my theory is, Steve, that anything that inert, non-living matter ends up doing as a function of its structure, we living things and I mean the whole continuum of living things, would have availability to. But we're all not the same living things. We've made different things available depending on our needs. So it's a more complex thing, but yeah, I would say anything that something not alive does in terms of functional structure, we could, any biological organism could recruit in service to survival. And Mariam, I think we have to look at your question later, and we'll definitely want Graham in on that answer.
Susan, the other part of that question, which I don't think you can see, is Stephen goes on to suggest occurring in biology. You can't see that because I answered.
No, yeah, I just see, that's interesting that I can only see some of it.
I think it's because I answered it privately.
I see. Okay.
So we got 2 minutes before Graham starts. So I just want to read some of the comments from Deb. Loved your presentation. Looking forward to more. From, I can't read the name. Well done, Susan. I really enjoy your demos and explanations. From Joe. I'm sorry, Joe, I can't pronounce your last name. Good explanation and demo of ecological psychology, Susan.
Joe Priscilla?
Yes. Yeah.
How'd I know?
Okay, great. So Graham, are you almost ready?
Yes, if I share, is that right?
You share. I'm going to pin your video. And Mariana, thank you for the tech support from WhatsApp. Anything else I'm happy to receive. Okay. That's been answered. Okay, we're ready, Graham.
Right, well, hello everybody. I'm an osteopath and biologist in Nottingham, UK, so we're all spread all over the place. And over the course of many years in practice, I recognised things in my patients that just didn't make sense. For example, the huge number of changes that follow even the simplest of movements seemed impossible to comprehend. And the way that every part of the body has an influence on every other part was something that I always took for granted, but was never properly explained in the textbooks. So when I read an article in an osteopathic magazine that described a different way of understanding the human body, the thing that really caught my attention was a picture of the Tensegrity Icosahedron, just like this one. And today, I want to show you why this model is so important and how it provides a better understanding of structural anatomy. Biotensegrity recognizes that complex living structures are the result of some interactions between some basic principles of self-organization, and that these extend from the smallest of molecules to the complete organism. Now, when I first started doing presentations, I would do my talk, and at the end of it, someone would say, how can I apply this to treatment? And it really stumped me at the time. I was really puzzled. And I had to go away and think about it. We've all been brought up with a traditional way of looking at science and biology. But the biotensegrity is different because it's based on first principles. And in a way, we need to completely unlearn many of the things we've been taught before and look at things in a different way, which is what Susan has been showing us. Some basic stuff. You think, how is ball bearings useful? But she showed how this is useful to understanding the structure. So I'm going to blast you with lots of information. Don't get hung up in the details. There's so much to discover. Go for the ride. Take the bits that interest you and look at it more. Hopefully it'll start to make sense, have a real meaning to what we do in our practice. So There we go. So over the course of our lives, we've all been taught that the body moves through a system of levers. But the problem with levers is that they generate bending moments and shear stresses and stress concentrations. And it is unlikely that developing tissues would be able to withstand the disastrous consequences of these. Levers rotate around fixed fulcrums, yet bones follow complex helical pathways during motion. In addition, the nervous system is incapable of controlling the huge complexity of joint movements on its own, which thus leaves a massive gap in our understanding. The whole idea of levers has been around for more than 300 years, since the mathematician Giovanni Borelli compared the anatomy of human movement with man-made machines of the day. And in 1680, he wrote a book describing his system of levers as an explanation for joint motion. And this idea has persisted ever since. Lever theory is based on the laws of classical mechanics, as formulated by Isaac Newton, Robert Hooke, Galileo Galilei, amongst others. But these rules were discovered on inanimate objects, and they don't necessarily apply to the nonlinear dynamics of living tissues. So what started off as a theory of human movement that has never been proved has become established as a principle of biomechanics simply because there has been nothing else to replace it, until now. There is nothing wrong with classical mechanics, but its application to biology is mostly contrived and out of date. Biotensegrity is different because it is based on the fundamental rules of physics first and from which everything else is derived, and thus represents a paradigm shift in the way that we think about the human body. It is a structural design principle that describes a relationship between every part of the organism and the mechanical system that integrates them into a complete functional unit. A simple re-evaluation of anatomy is a network of structures under tension and others that are compressed, parts that pull things together and others that keep them apart. Basic physics. The Tensegrity model is strong, light in weight, and flexible.
Graham, do you want to make it so if you go on to, if you stop your share, they'll be able to see you better.
Yes.
Right now you're just a teeny tiny little box.
Sure. Right. Is that okay?
Nice.
I'll go back to where I was, which is good. It can change shape with a minimum of effort and always returns to the same position of stable equilibrium. And its physical properties are very similar to living tissues. Each part is integrated into the whole. I'll go back a moment to this. Yeah. So there is a bigger. When one part moves, the whole structure moves and changes shape and enables forces, power, and information to be transferred from one part of the system to another in a controlled way. Yeah. At the most basic level, atoms interact with each other through the forces of a, At the most basic level, atoms interact with each other through the forces of attraction and repulsion, and they spontaneously organize themselves into the most stable and energy efficient configuration to form rigid crystals and flexible molecules, and the same principles apply at every size scale, where we now refer to these forces as tension and compression. Tensegrity models are representations of these invisible forces of attraction or repulsion, but now we refer to as tension and compression. Whether struts are suspended or appear to float, within the tension network of cables. And in the same way, we can think of bones as being suspended within the tension network of muscles, fascia, and other connective tissues, because both the simple model and the complex anatomy are formed through the same principles. The geodesic geometry, where these forces always act in straight lines, but give rise to complex curvature at higher size scales. And curvature is just another means of minimizing energy. The efficient packing of multiple structures into the smallest amount of space, where each one is a modular unit that is nested within all those surrounding it and dependent on all those surrounding it. And the principle of minimal energy, where everything happens in the simplest and most energy efficient way possible. Now in these models, the structure always settles into a state of balanced equilibrium, whereas the dynamics of living tissues are constantly changing and far from equilibrium. And if we look at some of the aspects of biotensegrity, which I'll have to wait for another lecture, we can see how living organisms can combine the tensegrity principles with non-equilibrium dynamics. That's for another time, I'm afraid. The person who put a biotensegrity concept together is the orthopedic surgeon by the name of Stephen Levin, who recognized things at the operating table that couldn't be explained by conventional biomechanical theory. And so he set about looking for alternatives by examining the skeletons of dinosaurs and other animals in the Smithsonian Museum of Natural History in Washington, DC. And one day he was sitting outside the museum and he looked across the mall to the Herschel Museum of Fine Art. And there, standing outside it, was a 60-foot structure called the Needle Tower by the artist Kenneth Nelson. And upon further examination, Levin realized that this model explained not only how the huge weight of dinosaur necks and heads could be suspended so far from their body, but applied to the whole of biology, and has been writing and talking about it ever since. In 1948, the then young artist Kenneth Nelson, one of the first people to recognize the importance of this new structural design principle, he described tensegrity as the physical representation of invisible forces. The physical representation of invisible forces, where the tension and compression are separated into the cables and struts, and they're all integrated together into a complete structural and functional unit. Arising out of this structure is a principle of heterarchical organization, which is inherent in the tensegrity model and ubiquitous in biology, where each part is made from smaller parts, which are made from even smaller parts, and they're all integrated together into a complete functional unit. Heterarchies provide strength and optimize the load-bearing ability, and they provide a mechanism for dissipating potential damaging stresses down through the structure and rendering them harmless. In this picture here, this is the knee here, so lower part of the thigh, dissection. We can see how each part has smaller parts in it, and if we had a microscope, we could go even further. Unfortunately, I have a picture that I wanted to show, and I forgot to put it in with a tiger. If I can get it towards the end, maybe I'll try it later. Now, textbooks generally classify anatomy into a hierarchical system of large important structures at the top, followed by smaller, less significant ones. But this is so misleading from a biological perspective, which is why heterarchies is so much more important. Where each, what's this? I'll turn
I'm
that
just
off.
checking out. Sorry,
right.
sorry, Graham. I'm just
Sorry,
checking. Okay, so sorry for interrupting you.
That's
We've
quite all
changed
right.
the screen view, and now you don't have to toggle back and forth. You can
Okay.
do your demos as is.
All right.
Okay. Sorry, everyone, about that.
That's all right.
Okay.
Yes, in anatomy and biology, every part is nested within all those surrounding it, just like these struts are nested within the tension network. Each part is just as important as every other one because it enables forces to be transmitted from the top down, the bottom up, from inside out, and in every direction, which is why heterarchies is so important, because it is more, the body is more than just muscles moving bones, but everything right down to the molecular scale is involved in that process. So we can think of cells nested within the extracellular matrix, muscle fibers nested within the endomysial fascia, and bones nested within the tension muscles, fascia, and other connective tissues. The principle of heterarchies then shows that treatment is more than just a local process. It has the potential to influence the entire body at every size scale. So, underlying all of that is a system of closed chain kinematics, which are widespread in engineering, ubiquitous in biology, and form the basic mechanics of tensegrity. They are the nitty bits and pieces that enable the structure to move in a controlled way. So, can I show this, or shall I go back to demo mode? This is a 4-bar closed kinematic chain mechanism. See the closed unit, where the movement of one guides and regulates the position and movement of all the others in the system. Provides a simple and efficient mechanism that enables the controlled transfer and amplification of forces, power, and information throughout the system. Kinematics is all about the geometry of motion, and the simplest shape that enables this is the 4-bar shape. The pantograph mechanism here is also a 4-bar that amplifies the motion.
Sorry, hang on, Graham. I'm learning how to change the view for everybody, and I think you went over to your PowerPoint and I had it blocked with you.
Okay.
Okay, so now, pardon?
Do you want me to go back?
I don't know. Do you guys want him to go back? Do you have a hands up? Oh, I don't know. Jen Britt raises her hand, so that means yes. Jen asked you to go back.
Okay.
So did someone else.
You can do it this way. See, the whole thing is guided. There's no question about which way to go. The whole mechanism of control within the structure itself. Now, closed kinematic chains have been known about since at least the 18th century and are well described in the jaws of fish. And here we see 2 simplified 4 bars where the muscles in the trunk of the fish move and cause the mouth to open, suck in the prey and close again within a period of just 25 milliseconds. And in the mantis shrimp that lives on the sea floor, they have these long, what are called raptorial appendages, which strike the prey with a force of 1,000 newtons within just 3 milliseconds, because these closed chain systems can move much faster than muscles can contract. There's a big drive to understand these mechanisms. The cruciate ligaments within the knee form this crossbar arrangement that guide motion of the femur and tibia in relation to each other during movement. These structures here are created by the artist Theo Jansen in the Netherlands, where they walk along the beach and are powered entirely by the wind. So here's an example of the mechanism. I'll get back a bit. where the 3 bars, the triangles, provide a stability, allows the 4 bars to change shape and guide motion. And these walk along quite happily, all on their own. It shows how simple structures can cause controlled movement. Okay. In the extracellular matrix and fascia, with these lovely pictures by Dr. Gambato, a surgeon in France who's got his endoscope inside living bodies during surgery. This is living structures. And when one part moves, everything moves. These are connecting everything together. There is nothing in the body that is distinct. When we get down to the microscopic level, there's no one point to say, this is a muscle, this is a blood vessel, this is an artery, this is a tendon. There's no point, you can see one and the other, but there's no point where you can distinguish them. Everything merges into each other. And they're all these lower pictures here. There's a closed kinematic chain. And here's the same one. When a bit of tension has been put in a certain way, it changes shape and it goes back to the same position. These are changing all the time. And in this model here, you can see how this 4 bar, you may have part of it missing because of the pictures, but so getting close to home. Legs of horses and humans form these 4 bar arrangements with multi-articular muscles that cross both the knee and ankle and guide and stabilize and regulate motion of the horse's foot. These are muscles. These are muscles here. These are the bones. And in the same way in humans, you've got 4 bars arrangements that guide flexion, extension of the hip and knee, and the knee and ankle. And these are important because they enable forces and power to be transmitted from one part of this body in a controlled way. Multi-articular muscles are particularly interesting because they're able to act over the full range of both joints at the same time, or restrict the motion of one whilst enhancing that of another. And their isometric contractions, where the muscles keep the same length, enable these forces to be transferred from one part to another. For example, if we jump from a standing position, we can't jump very high. But if we crouch down and then jump, we're using the muscles that cross both our hips and our knees to transfer power from one place to another down to the ankle to enable a much greater range of motion in a controlled way. And the same works for the fingertips. How rock climbers can hold onto the rock just for the tips of their fingers. The muscles in the fingers are not strong enough to the whole body. What is happening is that the whole body is harnessed to do the task in hand. Very, very clever. And talking about fingers, we can demonstrate even more. This is an example of the extensor tendon mechanism in the middle finger, using this 4 bar here called Winslow's rhombus, after Winslow, who described it in the 18th century. These things have been known about a long time, and suddenly they've become important from a biotensegrity perspective. Now, there are no muscles in the fingers to control extensor movement, because they're all found in the forearm and hand. What happens is, as these muscles contract, they transfer their power through the tendons to the extensor fascial network in the fingers. But instead of moving each bone on its own, they change the tension in that network, which switches the system between different functional states. So there's lots of different positions we can get our fingers into. There aren't enough muscles to do it on their own. It's because the system itself is processing information of forces and power and direction from the muscles and performing its own logic computations that were previously attributed to the nervous system. The whole body is an information processing system. Every movement we make, the structure itself is guiding that motion and operating in synergy with the nervous system. How are we doing for time? I can miss this one out.
No, you're good, Graham.
Okay.
Keep going. You got lots of time.
Okay. Two of the properties is a merge out of the particular structure, of which Susan's already mentioned, auxetic behavior and nonlinearity. The 4-bar structure demonstrates nicely this nonlinear process. Here we see a 4-bar here. If we measure the angles, if we measure the angles alpha and beta and plot them on this graph, we produce a nice closed curve. And this particular curve is characteristic of this particular shape. But each shape will be different and produce a different curve. Now, standard mechanics looks at a stress-strain relationship to be a straight line. But biological structures and tensegrities behave in a non-linear way and produce a curve similar to this. Whereas by normal biomechanics, consider the body operates in this region here, almost vertical region. It's so misleading. Living organisms cannot function in a linear way. It is much more likely that it will work in this more horizontal region here, the low stress strain region, because they will then be working more efficiently, optimizing what they can do. In addition, standard mechanics describes this curve here through what's called Young's modulus. It measures the rate of the curve, and they apply Young's modulus to here. They pretend it's a straight line, but it's not. The idea of Young's modulus in biology is complete nonsense. It should be just, if you ever read an article that mentions Young's modulus of some particular structure, they're looking at one point because it's going to be different at each point along the curve. A bit technical, I know, but I'm just passing it by you. In addition, the curve never reaches zero stress. There's always some intrinsic tension contained within the system. So Susan's explained auxetics. I'll just throw a little bit as an example. Living structures, when they're stretched, they get thinner in the middle. And when they're shortened, they're fat. Long and thin, short and fat. But living structures and tensegrity structures can behave differently. You probably, yes. Susan showed the tensegrity model. It's a bit small, maybe. Now, this isn't a tensegrity model. It makes the effect of everything expands and contracts around a single point. Notice all the little 4-bar, 3-bar chains in it that enable it to do that. Auxetic behavior is described in skin, tendons, bone, and other structures. It's well recognized, but conveniently pushed aside. Hopefully we can get it, with the help of others, to a more prominent position. Living structures are not restricted by the standard laws of classical mechanics, but conform more to the emerging field of soft matter, as Susan mentioned, and suggest that many of our ideas about biology are in urgent need of revision. So I've looked at some characteristics of biotensegrity on a quick example to show you how it's useful. The first one I want to show you is that of the elbow, commonly described as a hinge joint and third-class lever, where the bones grind against each other during motion. But this is complete nonsense. In addition, it is thought that the bones move through a system of flexor muscles and extensor muscles. This is also questionable. For example, one of the elbow muscles, brachioradialis, in the forearm, where are we? Yeah, forearm, is only active in rapid and forced flexion and extension. Rather bizarrely, which is supplied by the radial nerve, the nerve that innervates triceps and anconeus. Anconeus is also interesting because this little muscle is always active before the much larger triceps. And it is the only elbow muscle which is not directly attached to the overlying fascia, which suggests that something else must be going on. When brachioradialis contracts, it exerts a distraction force across the joint surfaces between the humerus and ulna in the direction of this blue arrow here. And this will be contained by triceps, anconeus, and the posterior fascia. So it may be that brachioradialis and anconeus work together as part of a rapid response unit. It regulates pressure across the joint surfaces, allows them to glide against each other without being compressed, or maybe maintain a certain amount of separation between the bones. Biotensegrity then explains how the bones can be suspended within the tension muscles, fascia, and other connective tissues, where the structures themselves guide motion. There are no bending moments, no shear stresses, no levers. And this particular model has now been taken up by NASA in development of new types of joint for both robotic purposes, but also prostheses with medical applications. And hopefully we'll see more of this in the near future. Second example I want to show you is that of the temporo-mandibular joint or jaw joint, also described as a hinge joint and third-class lever, where the bones compress the disc between them. But this is nonsense. If you look at any book, any article on the jaw joint, the first thing that they always say is the temporo-mandibular joint causes more problems than any other joint in the body and is the least understood. Then away they go with an explanation of the lever system to explain joint motion, knowing full well that a compressed disc will lead to pathology. But of course, until recently, there's been no alternative. Now, it is well known that the hyoid bone is suspended within the tensioned muscles and fascia. And this acts as a stabilizer. It allows the front of the jaw to be pulled downwards during mouth opening. Conversely, the mandible can be the stabilizer to allow the hyoid bone to be pulled upwards and forwards and influence the pharyngeal tissues during swallowing. Over the last few years, it's been recognized that a particular thickening of the cervical fascia called the mandibulo-stylohyoid ligament, which from a tensegrity perspective is really interesting. So what may be happening is, as the hyoid bone is stabilized, it's pulled downwards by the stylohyoid and omohyoid muscles. It tensions this ligament, which pulls the angle of the jaw downwards, which lowers the condyle and takes the pressure off the disc. The biotensegrity perspective then shows how the mandible and the hyoid are suspended within the surrounding muscles and fascia from a tensegrity perspective. It allows the bones to be placed in any particular position during mouth opening, during eating, during talking, with the nervous system acting in control at a high level. And this model has also been taken up by many dentists and orthodontists in development of new methods and techniques in the application of treating both the temporo-mandibular joint and the dentition itself. And we're going to hear a lot more about this in the near future. So, to conclude my little bit, we looked at some characteristics of the biotensegrity concept. We've seen how the same basic principles that operate on the simple model also operate in the organization of complex anatomy, where the forces of tension and compression are separated into distinct structural entities and all integrated together into complete modular heterarchy. Extends from the smallest of molecules to the complete organism. Biotensegrity is thus different because it is based on the fundamental rules of physics first and from which everything else is derived, and represent a paradigm shift in the way that we think about the human body. It is part of basic science that should underpin clinical reasoning. So in itself, what I've said doesn't tell you how to apply it in treatment, but it's a thing underlying everything we do. And we're just scratching the surface, just so much more to explore. So rather than just thinking of bones, muscles, and fascia as isolated, distinct structures, think of them as parts of body-wide closed kinematic chain mechanism, which couples every part into a unified whole and operates in synergy with the nervous system. Biotensegrity looks at morphological complexity through the geometry of its architecture and appreciates this as a simple and energy-efficient configuration as it refined itself over hundreds of millions of years. A constantly evolving information processing system that enables each part to move with a minimum of effort and powers a dynamism that we recognize as life. Thank you.
Thank you, Graham. I am going to put us into gallery view, I think. You could
I'll stop share.
Stop your share, yeah. And then if somebody can type into the chat box if the view is good, but I think they can actually, hang on, Susan, you're muted. Unmute, you can unmute yourself. So we've got some questions, and Chris, since this is on Facebook, we can get a copy of the recording. Graham, that's very good. This is from Deborah Chasey or Chasey. Susan, you're unmuted now. I'm just going to read to you. I loved your presentation, Graham. This is from Emily. Emily, please type your question into the Q&A. Anastasi, hi Anastasi, bravo to all three of us. Must fly, bye. From Kate, thanks. There's a whole bunch of comments that I'm not sure we'll have access to later or not. So you can look at them yourselves. And I have some questions for you. I think what we'll do is start, if you want to see them yourselves, Graham and Susan, you can click on the Q&A icon at the bottom.
All right.
I think we should start with Mariam.
Yes.
Moini. Her question is, I have a question about the tensegrity spine. It has been assumed several times that according to biotensegrity, there's no compression going through the vertebral discs and intravertebral discs. Well, there have been many studies in literature which concluded and proved that there is indeed pressure and compressive forces on the bones and mainly discs.
Lovely, lovely.
Actually, according to Wolff's law, without any compression on the bones, the vertebral bodies will become less dense and weaker. Is there any way to explain this in a more scientific manner?
Lovely, lovely question. There's so many things behind we'd want to know. First of all, if we're going to use mechanics most of the things in the body are done on cadavers, dead tissue. And you put a cadaver spine and do all sorts of things and stick probes in it to measure stuff, you'll get any result you want, really. As soon as you start to invade the body, you've changed things. Cut a little hole anywhere to put some probe in, whatever, you have changed the structure. Now, this is generally disregarded in the biomechanical world. Oh, it's not going to affect it much, and it gives us an idea and it helps. Yes, it gives you an idea, but the whole premise of it's assumed it must be under compression. No doubt there is some compression from time to time, but it's generally a tension structure. Tension and compression always operate together. And maybe occasions when things change. But it's so difficult to measure it in an absolutely concrete way, because as soon as you change it, anything, you destroy the structure. And so Wolff's law is not only about compression, but about forces acting on it. He also considers tension as well. So there's so many forces acting on those vertebrae. It's really difficult to know exactly what's happening. The tensegrity model, this is the thing. It's an overriding model. And if all these studies were done from a biotensegrity perspective, they'd probably come to quite different conclusions. But they've got their biases already set up in the first place.
Can I just pipe in?
Yes.
Yeah. So, I mean, because Miriam's right? I mean, about Wolff's law, without compressive forces in the body, there could be no bone, and there could be no tension, as Graham says. Tension and compression co-beget in the body, from my perspective. It's a yin-yang parallel emergence kind of thing. What we don't have, right? And I think this is what we're trying to say, is we don't have continuous compression, vertebra to vertebra.
Yeah.
That's what we don't have. It's not that the bones are not under compression. These struts are under compression. They're being compressed by the tension cables. The tension cables are being tensed by the compression struts. You see? And so it's not that we're saying there's no compression in the vertebra.
And
so I just wanted to make that clear.
Every step you take is spring loading the bones in this case. And Joe says that so bone can be a powerful free source of force for better or worse.
Look at how this oscillates and loads, transfers. Yes, I would agree. Steve talks about the bones being big springs in the body. So I hope some of that helps.
Yes, yes. Most biomechanical things are done assuming that it is fully compressed, and so their methods are flawed in the first place, unless they can show me otherwise, and I've seen nothing, no evidence that convinces me. It says type answer. Should I type this in, or will that?
No, but we've got
more
questions.
We'll answer some more questions, and I think we could maybe put these ones together from Yasmin Lambat. Is what are the invisible forces that shape our physical structure? So she's asking for a review of that. And Lisa Babiak asks, are cells an icosahedron or various platonic geometrical shapes? I don't think I read that very well.
Yes, you did.
Yeah. Okay.
That also relates to Carol's question, how does this model translate down to the cells, I think.
And I'd like to also add for Miriam, I think that there needs to be a clear definition on tensegrity models from all the people working with models. And I would add to that the difference between tensegrity and biotensegrity. But this is getting too many topics up on the floor at once, I think. So where should we start? You guys choose. You're answering.
Do you want to take one, Susan?
Well, let's go to the invisible forces that shape our physical structure. These are the invisible forces that shape all structures, not just ours. And that's why in my notes, I talk about understanding how things fall together and the nature of things. As Graham was saying, this is the attraction and repulsion, the electromagnetic attraction and repulsion that we see at the nano level, right, at the atomic level, translates as you come up through scale levels in the system and things get compounded eventually into these forces of tension and compression. So, well, there are 4, arguably, and I guess they found another one last year or something, maybe 5 forces at all in the universe. And gravity is one of them. And electromagnetic is another. And then you have the strong nuclear force and the weak nuclear force. The strong nuclear force and the weak nuclear force are the stronger forces, but they function at those micro nano levels. I mean, molecular and submolecular levels. So we don't physically deal with them so much. Electromagnetism and gravity, we deal with those. Those are weaker forces, but they're more in our lives at our macro scale level in which we live as material beings. So does that start us off?
All atoms interact with each other through forces of attraction and repulsion. There's different types of attraction. There's van der Waals and hydrogen bonding and electrostatics and covalency and steric repulsion. There are different types of attraction and repulsion, but they can all be labeled as attract and repel. And when we scale up to molecules, to tissues, whatever, we then refer to these forces as tension and compression, but they're just the words we use to describe them at that level. They're all doing the same principle, the yin and the yang, the attraction and repulsion, the tension and compression.
Yeah, so physically to feel them, if you push one arm against the other, it's push and pull. I'm pushing, and now you can interlock your fingers and pull. Everything's going to be a combination of those two things.
Cells and tissues form, or cells certainly function in relation to the forces around them. The forces acting on the cells cause them to change their function, to differentiate, to divide, to die, to move, whatever.
Yeah.
And they form tissues. The cells form the tissues which they move through, which then is influenced by the forces acting on them. You see, we can't see these things. It's a microscopic level. But understanding of that everything is all related to the same principles, which is Biotensegrity, explains that, gives us an understanding to work towards, understanding even more.
So I think, Carol, maybe that helps with your question too, but let us know if it doesn't. And then Graham, do you want to take this question? I don't know if you can see it from Lisa about are the cells icosahedron or various Platonic geometrical shapes?
Right. Yes and no. If we take an icosahedron, they don't look like that, no. If we take the tensegrity, so the tensegrity icosahedron, the principle here is that tension and compression are complete balanced. Yeah. So cells are like tensegrity icosahedrons. Now they don't look like that, but the same principle of balance of forces, even though they might be irregular, the same principle of balance of forces. The Platonics, like Susan demonstrated with when she first had the dish and the ball bearings in it, out of that you can get tetrahedron, icosahedron, and all sorts of different Platonic shapes. Occasionally you will find a structure that looks just like a Platonic structure, but that's almost coincidental. But because they're all formed through the same principles that form the Platonic shapes, these things are bound to pop out eventually, as they do in enzyme structure. So many enzymes have a tetrahedral or dodecahedral core shape about them. Collagen molecule is very much based on the tetrahelix that Susan showed, which I haven't got one, but the same principles of geometry. Um,
And
not-
when we see,
that's-
yeah, and when we see like viruses and stuff like that, there's a lot of organisms that are, they look very much like an icosahedron.
Yeah. And
Yeah.
there are backup. We have got backup references to justify all the things we're saying. If anyone wanted to explore more,
But it's sort of like, you know, I don't look like a cell,
no.
but I'm pretty confident I'm made up of cells, among other things. So extracellular matrix, It's more complex than that, but you know, grade school learning, we're made up of all these different cells. But when you look at me, you don't see, she looks just like a cell in a textbook. The building block and the building look different.
Yes, but they're formed on the same structural principles.
Yes, and the icosahedron, as Graham said, we're not saying we look like this. We're saying this is a force vector diagram.
It's a model.
It's a model of an energy interaction, of force interactions, and we are living force vector diagrams. What your shape is the result of all your many force vector diagrams, is your result of all your many force vectors and the things going on. Yes?
And I'll just add that I've just put in both of your emails and your contact information into the chat box, because people might want to follow up, Graham, on your offer to give them more, and Susan as well.
Can I make a quick comment to Carol Davis's?
Yes, please.
I'm not quite exactly sure what you meant by that, but whenever we touch the body, we have an influence. Just touching someone is a force, and that force will spread throughout depending on what the structure is underneath it. Now, cells, cancer cells, for example, also all moving cells that move, the mesenchymal cells within the body, fibroblasts, they move in response to forces, and they can detect, say a fibroblast can detect a myofibroblast some distance away and respond to it, because myofibroblasts are much more contractile, and these cells can relate to each other. So physical forces within the extracellular matrix through which the cells pass through is important to cell function. Cell function can go awry and cause cancer cells, which then do the business, do their stuff. So whenever we move, whenever we touch someone in therapy, we are influencing structure right down to the cellular level. We may not always be able to define exactly what we're doing, but the two are related. What we do is going to influence the cells and influence their function. The two are together.
Yes, if you look at the work of, we look at the work of Mina Bissell, Minabissell, I think it is.
Yeah.
And she studies cancer, and she talks about how they can change the shape, and then the tissue will revert back to healthy tissue from cancerous through shape changes. So geometry is really important.
Geometry guides the forces that pass through.
Yes.
And the closed kinematic chains explain the mechanics of how movement happens at every level, right down to molecular level.
So we end up talking about all these different things separately. Now we're going to talk about soft matter. Now we're going to talk about geometry. Now we're going to talk about oscillations. But the truth is, everything's coming together. Like an orchestra is playing a piece, everybody's playing together. But if you want to look at the music, you're going to see here's what the violin's doing, here's what the bass is doing. I just want to get back to Emily, question about the grapes. And yes, the point.
Susan, hang on. I'm
Oh,
just going to read the question because I don't know if other people can see them.
Sure, sure.
So this is a question from Emily McCullum for Susan. Example of the grapes and the can on the paper. Was the point that the moisture in living things stays bound in them? And thank you. I very much enjoyed your examples, just so that people know the question.
Yeah, thanks. Yes. And again, this is something that that Steve came up with, Steve Levin. And, you know, it's kind of brilliant because, I mean, when I turn these grapes over, they feel moist here. Okay. Mm-hmm. But there's nothing dripping into there's no water getting sucked into the paper towel. The moisture is in the tissues. And Steve also will show a meat grinder, and you can see the meat, you know, glistening as it comes out of the grinder. And, you know, there's no water, there's nothing dripping, but there's clearly a moisture to the tissues. So no liquid in the body, except like urine in the bladder or something like that, which is being held, but is already effectively outside the system. You know, no liquids, no solids, no gases, everything is soft matter. And we're not the only ones saying this. There are soft matter laboratories opening up and research institutes opening up at incredible speeds all over the world now. And you know, it used to say on the soft matter, I can't remember the school at Oxford, their soft matter school, that biology is soft matter come alive. So all of these soft matter schools that are new material science schools that are opening are including biology in their work. So even though in biomechanics, they're still modeling as if we were like solids or machines. They're not doing that in the biophysics labs that I can see.
Here's a great question from Mariana. Do you see it? If you vibrate the can on top of the grapes, does it change? Let's
vibrate.
Can you turn your yeah.
I'm going to sit this on a stable surface. Okay, so if I put this on the plate, the can just sits on the plate. You see me tapping it. If I sit it, it's a great question, Miriam. If I sit it on the grapes, get all that wiggling.
I think perhaps she's also wondering about how it changes the bound water in the grapes itself. Mariana,
I think we can't know. I think we can't know. I mean, we'd have to do things to be able to determine that.
So here's another project for you, Mariana. Let us know how it goes.
But we know there's a high amount of oscillation with very light touch in the system, in a tensegrity system. I think there was another one Miriam had about if you want to answer. Do you see that, Chris, from 317?
Yep. Do you want me to read it out? You've answered Emily. We've answered this. Emily goes back. Can we just stick with the grapes for a moment? Because
Sure.
You see, Emily says, what about the droplets of liquid that we can see in scanning microscopic images of fascia?
Can I?
Yes.
Yeah. Graham, take it away.
They're artifacts. They're artifacts. Well, the same with Jean-Claude Gambetto's pictures of the fascia and extracellular matrix, and you see lots of fluid droplets, but that's an artifact created by pulling the tissues so that you can see the structure inside. Because if you've got a drop of water, it suggests there must be a space around it, and there are no spaces in the body. everything is continuous. And if you, and I haven't seen these particular microscopic images, scanning microscopic images of fascia, but I suggest they're artifacts of the preparation process. May be very useful, but droplets of liquid, I'll be very suspect.
And Carol Davis adds that pressure and shear over the fascia, then removing the hands, Chatow says will pull water out of the capillaries, as well as contraction of muscle pulls water out into the fascia from the capillaries. But it's still bound water, no? Or I don't know.
Yeah.
Yeah.
I mean, my understanding is that it would all be bound water. It wouldn't be, if we use the word water like, you know, what can slosh around in a glass or be dripped from a teaspoon, we have taken ourselves kind of down the wrong road. And it's going to be bound water. It's going to be,
yes, bound in fascia. And, you know, I think this is also a response to perhaps Mariana's wondering about the grape, you know, what happens when we vibrate. So, yeah, just talking about the ability for the tissue to change depending on the environment or that it's in.
And these are such great questions. And guys, this is why we need more people doing research in biotensegrity. We can't do it all. So we need your curiosity. We need your perspective. We need your experience.
And do you see Emily's further comment about actually read the droplets of water? I guess the real question is how the grapes or the ground meat hold the moisture within.
The structure itself is
the structure, yeah, the biology. And this is where we study soft matter and the structure of soft matter. It informs us. Some people, it looks like, are entering their questions into the chat instead of into the Q&A.
Yeah, you're right.
So
and their comments too, because Kim's talking about bound water. Another example is Jello. If you jiggle it, the water doesn't pour out. If you squeeze it, you don't get drops of water.
Yeah, but if you touch it, it feels moist. Great, Kim.
Okay, so we've answered Emily's questions, yeah?
We have this question about the spine from 3:17 p.m.
Yes, go ahead, go for it. Do you want to read it out first?
Yeah, why don't you? And it's
okay. This is to both of you. If you want to answer one question related to the spine load bearing abilities using the biotensegrity concept, but in a more scientific way, what would that be?
Well, have you got something, Susan?
Well, the word that comes to my mind, there's a couple of ideas, is that, well, the word that comes to my mind is distribution. Okay. First, and part of that is just the idea of saying the spine's load-bearing abilities. If you touch me, my whole body is bearing that load. There's no part of me that's not bearing that load. And the more you push on me, the more my whole body is, let me say, we do this exercise with Tai Chi. It's distributing the force and it's taking it to ground. So we do an exercise where somebody can push, even on like your fingertips if you're standing, and they can push like a palm heavy weight or push on the arm. Some of you have done this with me. And I can even wiggle my body, you know, while somebody's doing that, the force, and I can stay relaxed, because what's happening is the force is being distributed through the entire system, and then it's going to ground. So I'm not really bearing it. I think the spine is not really bearing it. It's part of what's managing it, or just the forces of gravity and all that. But the whole body, everything's distributed. And I don't know how you would ever get inside a living body with a checklist and say, I see you're taking, oh, look, shoulder, you're taking 18% of that. It's all instantly distributed everywhere if we're integrated optimally, from my perspective.
Great. Can I add something more to that?
Please.
In a more scientific way.
Mm-hmm.
Well, we got a couple of hours talk here, but I won't go on that long. Science does the things it does. It has done for hundreds of years. We'll say a couple of 200-300 years, essentially, leading up to modern science. And it does things in a specific way. And when it comes to biology, there's a problem, because biological living tissues don't behave in a linear stress strain curve. When you stretch something, the response, the strain, isn't proportional to how much you stretch it or compress it. It is just, and because physicists can't accurately work with nonlinear dynamics, they discard it and say, we'll pretend it's a straight line. We'll take this little bit here and we'll call it a straight line, and then we'll get an approximate answer, and that'll be good enough. This whole basis of fudging a system, when we want to understand how the spine is loaded, we take a cadaver, stick it in a machine, put a weight on the top, and measure various bits. Or maybe with animals, they do all sorts of horrible things to animals by poking and prodding and stuff. Pretend that it's behaving like the real thing. That's supposed to be science. That's the way it's gone on before. Biotensegrity looks at it completely different from all the things we've been talking about, because you can't make these fudges. They're not scientifically valid. Everyone knows they're fudges and then forgets about them. So biotensegrity is an overall concept, a theory, a hypothesis about how the body, how living organisms operate. And if science was applied to test those theories, test the hypothesis, without going back, resorting to the old ways of doing experiments, we might get quite different results. Because it's the preconceived notions that have dominated standard method ever since Galileo and Newton. Great guys did some great stuff. Stuff is still relevant. But when it comes to biology, we have to look at things differently. And until I haven't got the equipment, the gear, until people really get on board on this, can do the experiments in the lab, which may not be able to answer the same questions as they thought they could before, but that is real science. But how we do real science in the biotensegrity concept, it's still being developed.
Yeah, and if I can add, I see a question from Lisa in the chat saying, how do we do this research? Now, I don't know, I know Daniel Roy registered, but he's in Australia, so he may be waiting to watch it online. But he's a Wing Chun practitioner and teacher, but he's also studying biomechanics at university now. I think he's at graduate level. I can't remember. I think he's going for a PhD. But the point is, they have footage of his teacher standing on a force plate, and then somebody else is pushing on the teacher. And then the weight increases. So then the teacher is taking in the weight, the pressure, and increasing it, but staying comfortably standing on one leg. They also, I believe, have it documented that he was on a force plate on one leg, somebody pushing on him, with a continuous force, and that the force was increasing, but that the weight did not change. Okay, So now that's a different thing that person's doing with their system, where they're, to my mind, meeting the other person with their ground reaction force from their body, bringing it up through to wherever they're being pushed upon. And I think they did another one with him, that same teacher who's no longer around, standing on a platform that had wheels, and then somebody pushing on the teacher, and the platform didn't move. So he was able to do something with his physical structure where there was a grounding through or a pulling up through or something, because typically if I stand on a platform with wheels and you push me, I'm going to be pushed. The wheels will roll. So this is the kind of, these are some places where we can do research. We can maybe get data. We're not going to be able to get inside the body necessarily and say this is doing exactly this and that is doing exactly that. But who knows what levels of understanding we can get to, or very often one question gets you, you know, this as a researcher, to the next. So those are some things people are doing that I'm aware of.
And I'll just read a couple comments to Graham's talking about the differences between what we have been doing and the new model. And that's, yes, this is from Carol Davis again. Yes, Graham, this linear model led to the randomized control trial. So completely false when collecting data from human beings. Like all human beings are alike, like every treatment is identical to the one before. Objectivity cannot be carried out from humans on humans with any meaningful results. And then real science is curiosity and taking good notes, also from Carol. And Miriam, I absolutely agree. Science becomes a culture by years, and no one wants to look at it differently. And then we have a thank you at the bottom from Yasmin. Can I just say, so we're to the end of our, just past our 90 minutes. And I just want to say to the people who are still on, I've put into the chat box for anybody who's interested. If you scroll down, it's quite towards the bottom, some links to sign up for MailChimp. Although if I can figure it out from your Zoom registration, if you checked, yes, I want to be on your newsletter, then I
There's
might.
one more question.
Is there?
Do you see it? Yeah,
Oh,
look in
I
the
saw that
Q&A.
one.
Yeah. I mean, if I have time, I don't know.
Okay, can I just finish this and then
Yes,
you can finish up
I
with a
just wanted to
question?
mention that.
I
Yeah.
just also want to let people know that there's a link to the YouTube channel that we're starting up. With any luck, this webinar will eventually be on YouTube. And there's also one for donations if people are interested in donating to the archive. Before we finish up, I want to thank everybody who's attended for being here and for sharing your passion, and for also sharing this work with other people and the links, etc. And to thank Susan and Graham for jumping on board on such short notice and bringing us this webinar. And now we'll go back to your question. It's from Lisa. Again, this is more a share. Do you want to read it, Susan?
Yeah, but I also want to say, Kim, I don't know if Kim Thompson's still online. This is about biotensegrity and pain. This is more a share. I'm going to be working with a psychologist that wants to research biotensegrity and pain with me. One of my students that has noticed there's something here that is different and needs to be brought to the forefront. If someone doesn't have access to this and academia is not open to another perspective, it is a challenge. Is there any other means to get this out? So Lisa, where are you again?
She's in maybe Calgary, somewhere in Alberta, Edmonton.
Great, because Kim Thompson is involved. You can see her in the chat. Maybe she can put up an email connection for you. Because Kim, you still work with is it called the Pain Institute? And you've put together conferences on pain. And you have an excellent understanding of biotensegrity. I would think that you and Lisa maybe should be directly connected.
Kim's put her email address in the chat box there, Lisa. So you can copy it and connect to her via email.
But let us know what you come up with.
Yes.
I want to be in on that conversation. I want to be the fly on the wall.
To the last part of the last sentence, is there any other means to get this out? That's one of the big challenges for us all. When anybody says, what's all this biotensegrity about then? And they want a 30-second answer, and which doesn't do it justice. So we're all working on ways to try and get this across to different audiences. The more we understand, the more we go back to the basics, the models, read the books, thinking about it, the more we can ourselves understand it better. And we're all in the same place, trying to understand it and try to express it in a way which is meaningful.
And I would also say talking about it with each other and building this community is very important. We now have Kim's email. Thanks for sharing, Kim. And Susan and Graham's email is also somewhere in your chat thread. So contact them with questions and keep up the conversation.
And Carol, it looks like Carol Davis should be part of that conversation on pain
And
as
here's
well.
Carol.
There she is, jumping in. Yes.
Thanks, Carol.
See, it's
So
better to use this as a jumping off point.
Yeah.
That's great. Thanks,
Great.
Chris, for putting this together.
Thank you so much.
You're welcome.